In the previous session, we started with the discussion of the propagation of the TE waves inside a rectangular waveguide. And we observed that I think that derivation was only half done. So let's quickly go through what we had discussed and then we'll proceed. Okay, right. So in case of a TE wave, we know that the EZ component is equal to 0, but HZ is not 0, right? So in the general equation of the wave, we can write as follows: del square hz equal to minus omega square mu epsilon times hz. That's the equation governing the wave propagation, right, corresponding to the TE wave. We'll substitute for del square and we get this equation. Okay, and later on we'll make sure that since the wave propagation is in the z direction, so dou square hz by dou z square can be replaced in the following notation, and I can bring the right hand side to the left to take a common term like this. Okay, so after that we write the h square, right? We replace that with h square to get this equation, and now this is general second order equation, right? So we directly go for variable separation method of solution. We have to assume that the solution should be a product, capital X into capital Y, denoted by equation number 2, and x is a pure function of x, right? Capital Y will be the pure function of small y, right? So this is what is the standard procedure in mathematics whenever we are applying the variable separation method, okay, to solve the differential equation. So substituting this in equation 1 gives this part, right? And we can see that in order to separate the variables, I need to divide by capital X and Y. So you see, I get a term containing only X, I get a term containing only Y, and a constant. So this is the standard equation, right? Again, we know that we have to assume that one of the term as a constant, second term is also a constant. So minus b square and minus a square we assume, such that the h square, which is the original term that is on the right hand side, we get that as a h square equal to a square plus b square. So why we assume like this? Because it has a standard answer, right? So the standard answer is x equal to c1 cos bx, c2 sin bx. Okay, very similarly, the y can also be assumed in the same fashion, right? C3 cos ay, and also I have another term that is C4 sin ay. So right, so always we are going to get the two terms, one in terms of a sine, one in terms of cos. Okay, should be multiplied by the constants. So that's the standard procedure which we already have studied in mathematics. So right now you see we simply apply that over here. Okay, right. So we'll write the complete solution x into y, because previously we simply assumed that in this case we are assuming the answer hz to be x into y, isn't it? Okay, so we did h into y, x into y, so substitute x into y whichever we got in the above part of this. So here we wrote x into y, I just substitute that like this. So now you see we have the unknowns, right? C1, C2, C3, C4 present over there. In case of mathematics, when we solve, we use something called as the initial condition, but in this is a practical problem, so no initial condition will be given, we need to derive them. Okay, so for that purpose we use what is called as a boundary condition. The boundary condition needs to be applied wherever you sorry, wherever you find a boundary of the waveguide, right? I can try to relate the variables, some of the parameters I can relate to 0, and that itself will become our boundary condition. Now we see I'm looking at the TE wave, so Ez has to be 0, right? But other components can exist along x and y direction. Okay, but at the boundary, some of those other components like maybe ex, ey, hx, hy, etc., which exist, right, they may become 0, right? So whichever equal becomes 0, I'll write that as a boundary condition. So we have the following boundary conditions. We started with few of them, right? Later on we'll continue from. So first boundary condition is that, right, ex equal to 0 at y equal to 0, because it's the lower, right? It's the lower boundary, right, which lies on the xz plane. right? Ex equal to 0. So y equal to 0 from x is equal to 0 to a. Okay, then we'll go to the second boundary, right? Which diagram we are referring, I'll quickly show you that so that you can recall uh, the boundary condition being applied to which diagram. Okay, I'll quickly show you that. This boundary, this is our the rectangular waveguide. So x is 0 to a along the x-axis, that is the xz plane. All right, so fine. So second one we are applying to the left side, right, wherever we measure 0 to b. Okay, let's quickly apply that. So ey becomes equal to 0. What is the condition there? At that point x becomes equal to 0, correct? X equal to 0. And what is the other condition? The y varies now. Okay, y varies from 0 to b. So which wall? Okay, I'll just write here for so that you can refer this whenever you read. So this is the bottom. This is the bottom side. Okay, I can say that this is whatever I wrote just now. I'm trying to imply that this is the left side. Left side wall, you can say. Right. Let's go to the third boundary condition. So the third boundary condition will apply to the top wall. So if you remember the top wall, the value of y is a constant, correct? Y is at a height. Throughout that wall, the y value remains same, isn't it? So this is how we write. So this is Ex equal to 0 at, see, y has a fixed value that is equal to b. And what is the range of x? Range of x is x starts from 0, goes till a. Okay, so this is, I can write the top side wall. Okay, then the fourth boundary condition. So fourth boundary condition should be on the right side wall of the waveguide. So let's try to write that. It is along, in this case, the y becomes equal, y component is 0. So Ey becomes equal to 0, right? It is happening at, what is the position of this right side wall? Right side wall is located at x equal to a. Okay. And in this complete wall, the y varies. Y starts at 0, that is the lowest part, and the highest part is b. So 0 to b, right? I am talking about the right side wall. Okay, so what we do now, we'll substitute these equations in our original equations, right? So what are the original equation? I'll try to write the equation here. So these are the boundary condition, right? Let me try to write applying the first boundary condition to, I'll write the equation also. Okay, to the, we had one equation, that is Ex is equal to minus of gamma divided by h squared dou Ez by dou x minus j omega into mu divided by h square dou hz by dou y. Right, this is the standard equation of, it can be any mode, right? Any mode of wave that is propagating inside the rectangular waveguide. I'll quickly show you the equations also. What you see, we have equations like this. Okay, dou hz, right? We have 6 total equations derived, right? 3 equations corresponding to, right? You can see here, right? This is equation number 3, right? We have 3 equations coming here, and also we have 3 more equations coming, right? So these are the other 3 equations. I can get the equations Ex, Ey, Ez, Hx, Hy, etc. So 6 equations are there, out of which one of them I'm taking here. Ex equal to this. Okay, this is what is there, in which I'm trying to substitute the first condition. Okay, so that is first boundary condition, ex equal to 0 at y equal to 0 and x is 0 to a. So since x varies, I cannot actually write that, right? So I cannot write the y value over there. I'll put whatever, when x is equal to 0, I'll try to put that over there. Okay, right? So I know that Ez equal to 0. So first term is 0. I'll just make it 0 here itself. I will not substitute. Okay, first term is 0. This is obviously because Ez equal to 0, right? Only the second part let us substitute. So that is, this implies the Ex should be equal to, it is minus j omega mu divided by h square into, it's a partial derivative, so dou by dou y of the hz component. Okay, hz we have just now written in the previous section, that I'll show you. Just before this, you see hz is this whole equation, right? In which my intention is to find out the C1, C2, C3, C4, right? In that I'm trying to substitute. So this is dou by dou y of hz. Let's substitute. So we have two terms. One is a C1. It's a term containing x. So C1 cos bx plus C2 sin bx. First term, take a product with C3 cos ay plus C4 sin ay. Right. So now we can see that x varies, but y is equal to 0. In our case, right, in this particular, the first case, y is equal to 0 and x becomes equal to 0. So that's my term here. So what we can try to do now, what is the substitution, right? When I make this 0, so when I apply the condition, left hand side becomes equal to 0. Is it okay? Right. I'm applying the boundary condition. So this is equal to, right, I can write minus j omega mu by h square into, take a derivative with respect to y. So this c1 cos bx, c2 sin bx is a constant for us. So I'm not going to touch that. I'll keep it as it is. So that is c1 cos bx plus sin bx. All right, so that's my term, into, take a derivative. It's a dou by dou y of this term. So this becomes minus a times c3. Can I write sin ay because it is a differentiation? Plus, it's a differentiation once again. So a times c4 cos ay. Okay, in this again I can see that the y term becoming equal to 0. Right? So since y is equal to 0 according to this condition, this term is 0. Right? So now I see that. Anyway, okay, I'll try to write a simplified version. So these are the constants. So there is no meaning in equating them to 0. Right? So I'll write, this implies 0 is equal to, I have C1 cos bx. Yes. Right. So we have a into C4. Correct? And y equal to 0. So cos 0 is 1. So I just have a times C4. Okay, now I understand that the x actually is a variable. Sorry, just a second. Yeah. So x is a variable which varies from 0 to a during this. So since x varies, this whole term cannot be equal to 0, right? Because at a particular point when x equal to 0 or x equal to some point, the term may becomes equal to 0. But it cannot be, I cannot make a statement that, yeah, I cannot make a statement that it's completely equal to 0, right? Right. So because of that reason, only term, right, that I can equate to 0 here is equal to, this implies, right, the C4 becomes equal to 0. So as soon as the C4 becomes equal to 0, I can update, therefore, right? So this implies I can write the HZ component and as follows, right? We have the C1 cos Bx, C2 sin Bx into, now C4 is 0, so I can write C3 cos Ay. Is it okay? Right, let's hold on to this equation. Let me check the equation number for this. One, two. Okay, let me call this as equation 2. Then all the boundary conditions are named according to that. So boundary condition 1, 2, 3, 4 we have. So now I'll apply boundary condition 2 to this one. Okay, so before that, let me call this as equation number 3. Right, so let's try to apply the second boundary condition. Applying the second boundary condition. So the second boundary condition says that Ey is equal to 0 from x is equal to 0 and y is equal to 0 to b. Correct? So using that, I'll try to apply this to the Ey equation. There is a component called Ey which can be written in the following fashion: minus gamma divided by h square dou Ez by dou y plus j omega mu divided by h square dou hz divided by dou x. All right. Again, in this particular term, I don't have the Ez component, so this is equal to 0. Right? I just have to substitute to the term that is on the right side. Okay, so this implies, let's apply Ey is equal to j omega mu divided by h square into, I should perform the partial differentiation with respect to x. Dou by dou x of, let me write the hz as it is, later we'll simplify. So that is C1 cos Bx plus C2 sin Bx into C3 cos Ay. So this has to be differentiated with respect to x, then we'll equate it to 0. All right. So that means, let me simplify first. So Ey, what happens to Ey? Ey is equal to 0 actually, right? So 0 is equal to, right, j omega mu divided by h square into differentiate. So partial differentiation with respect to x now. So the first term is minus b into c1 into, this is a sin bx. Are you okay? Plus the next term, sine differentiation is cos. So b c2 cos bx. That's the first term. The second term remains as it is, no change. So that is c3 cos ay. In this, I have to apply the boundary condition that x equal to 0 and y actually varies from 0 to b. Correct? So when this happens, just find out what's the equation I can write. Anyway, j omega mu by h square, right? You don't have to write. So x is 0, so sine 0 is a 0. First term is not there. Only the second term will come into picture. And cos of b into 0 is cos 0, which is 1. So you see, you have the term that is bc2, okay? bc2 into c3. Then I have cos ay. Is it okay? Cos ay. So I can see that the cos ay is not 0, right? It cannot be equal to 0. Okay. So again, I cannot make the C3 0 because you have a C3 into this term, right? Actually, we moved that term to other side and we made it 0. But fundamentally, if you see that, right, I cannot make C3 0. If C3 0, everything becomes 0. Correct? Are you able to understand that? I cannot equate C3 as 0 now. If C3 0, this whole term is 0 always. Correct? Because it's a product. And I know that this term is not 0 always. This term is 0 only at the boundary. So again, right, I'll write the condition. Because of this, I can say that the C3 is not equal to 0. Right. When C3 is not equal to 0, this implies only term which you can say equal to 0 is C2. C2 equal to 0. So just remember why we are saying that C3 is not equal to 0. That's the important thing. Okay. Other than that, everything is straightforward. Okay. Right. Now let us try to update. This implies the HZ component gets updated in the following fashion. HZ is equal to C1, C3. We have cos Bx, cos Ay. Only these are the terms left over. So let me call this as equation number 4. Now I'm going to apply the boundary condition number 3. Apply the boundary condition number 3, right? To the equation which I'm going to consider now is Ex. Ex is equal to minus gamma divided by h square dou Ez divided by dou x minus j omega into mu divided by h square times dou hz by dou y. Is it okay? Right, in this again, I know that this is 0, so I don't have to consider that part, right? Simply let us substitute the given equation over there. This implies the Ex becomes equal to minus of j omega mu divided by h square into the partial derivative dou by dou y of the hz component. The latest hz is in the following format: c1 c3 cos bx into sine not sine, sorry, into once again cos ay. Okay, let us differentiate this with respect to y first, and then we'll equate to 0. So left hand side becomes equal to 0, right? This is minus j omega mu divided by h square into, take a derivative. So we have c1 c3 as it is. So cos differentiation is I think cos bx remains as it is, only it's with respect to y, right? Okay, so this is cos bx as it is into differentiation of cos ay is minus a sin ay. So this minus cancels with this minus. Okay, so final term I can write the term which I want to equate to 0 is only this part. 0 equal to constant, I'll remove. I have c1 c3 into capital A cos bx into sin ay. Okay, now let me bring the boundary condition here. Boundary condition is applicable at y equal to b and x equal to 0 to a. So x varies, so I cannot equate cos bx to 0. It's a constant, so sin ay, whenever I have a sin ay, right? Under what condition sin ay becomes equal to 0? It is not equal to 0 because sin ab, the term becomes equal to b here, right? So this is not 0 because it is actually sine of a times b, as the y takes a value equal to b. Correct? Y is equal to b now in this case. So anyway, I cannot equate that to 0. So capital A is not 0. C1, C3, right? Again, we have no clue as of now, right? Which one to make 0, right? So as of now, I cannot make it to 0, right? But I can think that maybe a cos bx, some cos bx tends to be 0. Is it possible? No, sorry. I think I made a mistake. I'll just rectify that. Just a second. I have written properly. C1 is not 0. C3 is not 0 as of now because we don't have any clue. Both of them I cannot take into consideration saying that it is equal to 0. Okay, capital A is also not equal to 0. Cos bx is also not equal to 0. Sorry, I think I made a wrong statement earlier. I'll correct. Okay, so cos bx, you cannot say that that is equal to 0. Why? Because x varies. Same reason we discussed earlier. So that means only the sin ay part has to be equal to 0. Okay, so I'll write it once again. This implies 0 is equal to C1, C3, capital A, cos Bx. Just a second. Okay, so that means I can write this is capital A times, I'll write cos Bx. Okay, A times cos Bx into, you see, I'll write sine of AB. Okay, because y is equal to b. So in such condition, this means I can have only one term that is equated to 0. It is sine AB equal to 0, right? So under what condition sine AB becomes equal to 0, right? This means AB can be equal to 0. It can be pi, it can be 2 pi. In general, it can be n pi. So I know the values of small b, but I don't know capital A. So that means capital A has to be n pi divided by small b. Okay, so that's what we call as equation number 5. Then, so third boundary condition is also over. Apply the fourth boundary condition, right? Apply the fourth boundary condition. And you are going to apply this boundary condition to the equation of EY. So EY we already have derived, that is given by minus gamma by h square. It is partial derivative. So dou Ez divided by dou y plus j omega mu divided by h square times dou hz by dou x. Okay, so that's our equation, in which again I know that this is 0. That is 0. Ez is 0, so no partial derivative, right? I will substitute, since I have not updated the equation in the previous case, I'll simply bring it back. Okay, so that implies the Ey becomes equal to, this is j omega mu divided by h square, right, into partial derivative dou by dou x of the hz. Hz is equal to c1 c3 cos bx into cos ay. All right, now I should differentiate this with respect to which variable? It is x. Okay, dou by dou x. Right, so let us try to differentiate first and then substitute the values. So j is equal, j omega mu divided by h square. Differentiation, I think we have c1, c3 as it is. Then cos bx should be differentiated. That gives you minus b sine bx into the cos ay as it is. It's a product. All right. So apply the boundary condition. A boundary condition says that left hand side becoming equal to 0. Right. So this is my condition, and the condition says that y varies from 0 to b. Okay, and x is equal to a. So x equal to a and y varies from 0 to b. So I cannot eliminate cos ay. I cannot equate that to 0 because y varies. All right, and c1 c3 b are constant, so that means it has to be sine ba equal to 0. That implies 0 is equal to, I'll write once again, minus c1 c3 b into sine of ba, because x is equal to a, into cos ay. So in that term I cannot equate all other terms to be 0. Only the sine of ba should be equal to 0. So when this happens, I can say that the BA is equal to 0 or pi, 2 pi. In general, it is n pi. Since n is already used, I'll use another number, m pi. Okay, so that means okay, sorry, I know A, so I cannot write A equal to. Let me try to find out the value of capital B now. So that implies, because capital B is unknown to me, right? Okay, so that means we can write it in the following fashion. This implies the value of capital B should be equal to, this is m pi divided by A. So I'll call this as equation number, say 6. So substituting this back, right, I'll try to write a complete solution now. So therefore, right, hz, this is the most recent update whatever we have, that is C1, C3, sorry, not C2, C2 and C4 we equated to 0 earlier because of the certain conditions. So I have C3 with me, C1 C3 into capital A cos Bx cos Ay. Okay, is it fine? Okay, now also we have the equation 5 and 6 with us, right? So let me call this is equation number 7. So 5 and 6 in 7. So we know that that gives hz as a proper equation, that is a C1 C3 into, this is cosine value of it is Bx. So we know that B has been substituting as we, so far we were substituting capital B, but now we'll write the value of B which is obtained in the equation number 6. Okay, so that is m pi by A into x, that's a constant. Okay, into second term is, oh, that's also cos. So into cos, I should write the A value. So A is n pi by B into y. All right, so what we can write here, now we can bring the constant term into picture, right? So this is also equal to hz is equal to some constant c, overall constant, okay, into cos m pi by A into x into another cos function, this is n pi by B into y. Now I know that I can bring the other components into picture. This is the hz component only. Okay, so equation number 8. Now try to recall what was the step we did after finding out the Ez in case of a TM wave. Perfect, that's the right answer. So we are supposed to multiply by the e to the power j omega t term, right? So to take care of the time, right? To take care of time and the axis, or axis along which it moves, right? So multiplying. So what we do now is we'll multiply the whole equation by the two terms, right? One term corresponding to the time. So what is that term? It is e to the power multiplied by the e to the power maybe j omega t, correct? Right? To consider the time, and you also multiply by e to the power minus gamma z. Why do you do that? To consider the direction of wave propagation, right? So when you add both of them, what happens now? We'll get the final equation of hz. So hz is equal to a constant c into, this is cos of, this is m pi by A into x into cos n pi by B into y. So many times I have to multiply by e to the power j omega t into e to the power minus gamma z. I'll club them, okay, minus gamma z. So this is the required equation. I think this is equation number 9 for us. That is the equation of hz, right? What is the z component of the magnetic field, right, which we can use, right? So that we can write. So this hz exists, right? The wave is propagating in the z direction and hz also exists over there, right? So because of that, now we are saying that, right, this is transverse electric wave, not magnetic, because magnetic component exists. Electric component is not there. Ez is equal to 0, so this is TE wave, right? So what we'll try to do now, we'll try to find the equations of other field components, right? So to find the field components of the transverse electric, what you do, we already have the equations, simply keep substituting the terms. Okay, so Ez is equal to Ez is 0, I can find Ex. What are the terms you need to find out? Ex, Ey, Hx and Hy. Okay, so I'll start with the Ex part. Ex is given by minus of gamma by h square. This is dou Ez divided by dou x minus j omega mu divided by h square into dou hz divided by dou y. All right, again, this is not there. I don't have to write this, or substitute only the next half, minus j omega mu by h square. Only that term you write, but don't write equal to 0 on the left side. It's not 0. It's not a boundary condition. Right now, we are inside the waveguide. Okay. So this is Ex. Ex is equal to, right? So you see, I am trying to differentiate this term with respect to y. Okay, whatever equation 9 we are seeing above, right? Only that equation I'm trying to differentiate with respect to y. So cos n pi by b into y is the term which gets differentiated. So n pi by b comes out, cos becomes a sign, minus sign. So minus of minus cancels. So you see it's positive. So my equation is, you see I'm directly writing the answer. Let me know if you have any doubt. Okay, j omega mu divided by h square, which is the term present, into the constant c. When I differentiate, I am going to get this term as a constant, that is n pi by b. Okay, look at equation number 9 and differentiate that with respect to y, and I am writing this answer. Okay, into, so first term is constant, so I have cos of m pi x by a, and the second term already is whatever we have is differentiated, and we get sine. Cos differentiation is minus sign, minus is already taken care of, so I simply will write sine of n pi by b into y. Okay, then the e to the power remains as it is. You are not going to differentiate. J omega t minus gamma z. All right, so that is equation number 10. This equation is the electric field component along the x-axis whenever the wave propagated through the rectangular waveguide is a transverse electric. You see, now this gives you a more clear answer to your question, right? Where, how the terms get terms be taken care of, right? So previously we made it 0, but now you see mu is there, right? So this mu will be mu naught into mu r. Whenever I bring any medium of certain mu r, it will be taken care automatically. Is that fine? Okay, right. Let's move further. So next is I need to find out the other field components as well. So what I do, I'll move to the second field component. Let's say I want to calculate the EY. EY, we have a standard equation already derived. I'll simply use it and I'll substitute the values. Minus gamma by h square. This is dou Ez divided by dou y plus j omega mu divided by h square times dou hz by dou x. So I put 9 in this equation. So this is 0. Ey becomes equal to, I am differentiating the cos term. So I am going to get a minus sign at the output. Minus sign. So minus I'll write outside. Minus j omega mu divided by h square into, there is a constant c. And since you differentiate a cos term, cos of m pi by a, the m pi by a will come out. M pi by a. okay, into cos becomes minus sine. So this is sine of m pi x by a into second term was a cos, it remains as it is because it is a function of y. Okay, n pi by b into y, then you write the e to the power j omega t minus b gamma z. So equation number 11, you see now this is the electric field component along the y-axis of a transverse electric wave propagating inside a rectangular waveguide. Okay, similarly we need to find two more. Okay, so the next one I'm going to write is for the hx component. Hx component has a very standard equation, and the equation we already have derived is minus gamma divided by h square into dou hz by dou x. This is plus j omega epsilon by h square into dou Ez divided by dou y. So now I can see that this term is 0, Ez is 0, so this term is not going to come into picture. Only let's write, substitute and differentiate that hz component in the first half of the equation. Okay, so there is dou y dou x of hz. Hz has to be differentiated with respect to x. There is a cos term which becomes minus sign. Okay, there is already a minus sign at the output, so this simply becomes gamma by h square. Minus minus cancels into a constant c times m pi by a into, okay, so no x now because differentiated, I already differentiated this with respect to x. Okay, into cos becomes minus sign, minus is already written, so this is m pi by a into x into, this is cos of n pi by b into y. Then write the terms as it is, that is e to the power j omega t minus gamma z. So this will be equation number 12. You can see that this equation, this is the governing equation corresponding to the magnetic field component along x-axis when a TE wave, that is transverse electric wave, propagates through the rectangular waveguide we considered. Is that okay? That is Hx. Similarly, let's move further and write an equation for Hy. The standard equation of Hy in rectangular waveguide is minus gamma divided by h square into the dou hz divided by, this is dou x, dou hz by dou x minus, let me just check the equation once. This is with respect to y, sorry, not x. Denominator is with respect to y. So this becomes now dou z by dou y minus j omega epsilon divided by h square into partial derivative dou Ez by dou x. So substitution by differentiating with respect to y. Okay, there is a cos term, cos of n pi by y, n pi by b into y. It becomes minus sign, so minus minus cancels. So this is gamma by h square. Then we have a constant c. Differentiation actually yields a term that is n pi by b because that's the term with respect to y. Okay, into cos of m pi by a times x into sine of n pi by b into y into e to the power, this is j omega t minus gamma z, equation number 13. So we have all the 6 components with us. Okay, so what are the 6 components? Let's start with the type of wave. The type of wave is transverse electric. So as soon as I'm saying that transverse electric, hz Ez is equal to 0. Very important, very first thing, right? Ez is 0, but hz exists, and hz is given by the equation number 9. Okay, this is hz. So 2 components you already know, right? Then the remaining 4 field components, that is Ex, equation number 10, Then EY, equation number 11, right? HX, magnetic field along x-axis is 12 and magnetic field along y-axis is 30. So these are the 6 components we are supposed to find out in case of a transverse electric wave propagating inside the rectangular waveguide. Okay, complete derivation. Right. So recall, in addition to the equations, when we discussed the TM wave, we had the various modes present in the rectangular waveguide. Okay, so let's write that. So various TE modes. So when you say modes, you are going to substitute various values of M and N. Okay, what are the various M comma N values you can substitute in the equation? Okay, so let's start discussion about that. So just tell me whether TE00 exists or not in the above equation. I'll show you the equations also. Okay, so just see these equations and tell me whether you can put M and N both are 0 0. So you need to identify what's going to happen when both M and N become equal to 0. Just see these equations. I'll show you the other equations also now, because we need all the 6 equations to make a decision. So let's start from the last and see, right? What I can I substitute M and N 0? So you see here, in this case, N is equal to 0 means equation is, N 0 means equation vanishes. Hy becomes 0. So, right? Let's see. Okay, so Hy will not be there. When N is 0, Hy is not there. When M is 0, Hx is not there. Let's go ahead. Check the equation number 11. M is 0 means Ey is also not there. Okay. Ex is also not there. Correct? M and N both are 0. Yeah, because right now I am trying to trace out all the 4 equations will not be there. Also, I'll check whether Hz is 0, right? Okay, so that's fine. Ez is anyway 0, correct? Ez is 0, right? In that case, right, only one component remains that is not sufficient for wave to propagate. Okay, so that means it does not exist. One of the 4 components should be there. Okay, or if you remember the fundamental we studied in the what do you call, the electromagnetic waves, in order to propagate a electromagnetic wave you need at least 2 components, any 2. Okay, only one exists means no, you cannot. Okay, let's move further. So part B, my question is, check whether TE, transverse electric 0 1 mode exists or not. It means M is equal to 0, N is equal to 1. Let me show you the equation. So N is 1, so I think Hy will exist. And which is the other term that exists? Can you check once? Okay. What about Ey? Okay. What about Ex? Yeah. So we understand that this implies Ey, right? Ex and Hy, correct? Right. So Ex not equal to 0 and y not equal to 0. So this means T01 exists. The wave will exist. This mode, yes, it can propagate. All right. Next, see, I'll try to go for TE10. It's a reverse, right? So we can write uh, Ey is not 0 and Hx is not 0. So overall, I can say that this particular mode exists in our case. And let's proceed further. The next is D. I want to check TE11. right? So the wave exists. So my conclusion is that, right, for any value of m greater than 1 and n greater than 1, m greater than or equal to 1 and n greater than or equal to 1, right, higher modes exist inside a rectangular waveguide corresponding to the transverse electric wave.